And, everything okay? Okay, great. Then, yeah, I guess let me start. Oh, I see it's recording started, so awesome. Welcome, everyone. I'm happy to see all of you here. I would like to tell you today a little bit about how to get started in quantum computing without necessarily having a PhD in physics, though I have to say a PhD in physics always helps. So my name is Michał Stęchły, and this is Zen for Quantum Meetup. And I wanted to thank the organizers for inviting me, for having me here, and just like for organizing this whole event. So I will not be able to see the chat because it will be super distracting for me to checking the chat. So if there are any questions, any issues, well, I hope someone will tell me. But yeah, like don't expect me to read the chat in the real time. Okay, so I hope this will last around like hour, maybe a little bit longer. We will see how it goes. The plan is as follows. So I will start with my personal story because I will tell you why. Then I will tell you why I think quantum computing is hard and why it matters that it's hard. Then I will share with you a couple of techniques how to learn. Then I will also touch on like professional development. So, how to build your career in quantum computing. And lastly, I will just like summarize the main points. And if we'll have time for some Q&A, I will be more than happy to answer your questions. Okay, so I'm not sure who exactly is, registered. So I assume you are a group of people who are, interested in quantum computing, who have some experience, some expertise in either science or engineering, and who would like to learn more about quantum computing. So that's just one thing. So that this presentation is mostly about people who are not, experts in quantum computing. Though I hope if you are an expert, you can also take something out of this. Okay, so I will tell you my story, and I will tell you it because I think it's important for you to know why I'm talking, why I'm telling you exactly the things I'm telling. It comes from like my background, my experience, and if your background is different, well, some things might not work as well as they did for me, or some things might be much easier for you or much harder. So just like, take that into account and be aware of that. So I'm from Poland. I did a bachelor in physics and a bachelor and master in automation, control, and robotics, which was pretty broad engineering. I work in sales and marketing for 1 year in my friend's company, but well, I wasn't particularly good salesperson, so stopped doing that. Then actually at the same company, I worked for 6 months as a Ruby on Rails developer, so web developer. After that, I joined Estimate, an incredible IoT startup in Krakow. And I had a position of software engineer / researcher, which basically meant that for some time, first I was developing new algorithms or improving the old ones, and then I was implementing them in production environment. So I had a little bit of research and a little bit of software engineering. And even though I never kind of had opportunity to work in machine learning or optimization, mathematical optimization strictly, I always had huge interest in that. I did some courses, I even taught some courses. So that's basically my background. When it comes to quantum computing, actually my whole quantum computing education at that point was 1 week, one course at my university, which was like 1 semester long at physics. And I got into like 5-day summer school about quantum computing in Innsbruck, where I kind of learned it a little bit more from the experimental physics side. That was in 2014, I believe. So now let's go to like the second part of my story, which is, well, how I got into quantum computing. So you can read about it more on my blog. I've written like blog posts with this whole story. In general, I have a blog, and I will be referring to some of my articles throughout this talk because they go more in depth on like specific topics. So in late 2017, I started to think, well, that perhaps quantum computing is an interesting career choice. So with my wife, we knew we would like to move abroad. So I knew I will have to change my job. And I decided, perhaps I might even change a field. So, well, I've heard that quantum computing, starts to be some like more real, not really, theoretical or think of like experimental physicists, but also like something slowly getting practical. So I decided that it's worth a shot. I did really I spent a substantial amount of time doing market research, trying to see what companies there are, where they are geographically, what kind of people these companies are looking for. And I decided that, well, the best way for me to proceed would be to do a project. And well, this project will allow me to like learn more about quantum computing and build some portfolio. So in March 2018, I started a project about solving traveling salesman problem with quantum computer, and that was with a startup, Board Technology. And yeah, I implemented it, finished it in June, and in July, together with Bohr, I went for the Creative Destruction Lab workshops in Toronto. So these 2-week workshops were part of 2-month like training by CDL. I was only for those 2 weeks of technical workshops. During that 2 weeks in Toronto, so that was like 14 days, I met with people from, I think, 6 different companies. And basically every other day I was talking with someone from some company. It's like I was looking for a job and, just asking everyone around whether they have a position that I could fit. In the end, Bohr offered to me like full-time position. So I started to work with Bohr, quit Estimate in July. Yes, in July. And from September, I started with Bohr. I was with Bohr until April 2019, when unfortunately Bohr closed. So again, I still was in Poland. My kind of immigration procedure to Canada was like still in progress. And fortunately, I've heard that Zapata Computing is opening an office in Toronto. So I decided, well, let's give it a shot. I had a couple of interviews. I went to Boston to talk with Zapata team, and finally I got a job as quantum software engineer at Zapata Computing. I started remotely from Poland in July, and in October I moved to Toronto, and since then I live in Canada and work at Zapata Toronto office. So what I do now, what I do now, right now, I'm pretty active in the space, I would say. I work as a quantum software engineer at Zapata Computing. I'm doing mostly, building Orchestra, our product platform for doing quantum computing. I'm implementing different algorithms and, helping with various research projects that we have at our company, mostly from the software side. I like to say that sometimes one of the things I do is just like taking a scientific paper and translating it into code. Another organization I'm working in, like affiliated with, is Quantum Open Source Foundation, where I'm running QC mentorship program. So that's basically a program where we are pairing people enthusiastic about quantum computing with a mentor from either academia or some companies. I also involved in Q for Climate. So this is about figuring out how to use quantum computing for solving climate-related problems. And we are in a very like early stage here. And also I have a blog called Musty Thoughts, where, you know, from time to time I write something, and usually about quantum computing. Okay, so that's like enough about me. I hope this gives you a good like overview of like who am I, and I'm like, you know, a software person with some research background, but definitely yeah, no, I don't have PhD, as you could notice, but I do have some background in physics. Okay, so what to expect from this talk? As I said, I don't expect that you will be able to just take 100% of what I will be talking about and apply it to your life. I guess there will be some nuggets of wisdom that will be useful for you. And also, like, be aware that, you know, if the more close your profile is to mine, probably the more you will take out of this. I still try to be general enough so that everyone can learn something from this. But as I said before, you know, not everything that I say must necessarily work for you in particular. Okay, so okay, so the important question is, like, is quantum computing intrinsically harder than other areas of science? So is quantum computing harder than, let's say, machine learning, or is it harder than physics or general relativity, or I don't know, computational chemistry? So I don't think so. I think it's hard, you know, there's no metric for comparing how hard given discipline is, but I don't see a reason why quantum computing should be like intrinsically harder than like other disciplines. However, another question, like, is quantum computing harder to learn than other subjects? Well, I do think so. And there are a couple of reasons for that. And I believe that understanding the reasons why quantum computing might be hard to learn might help you like make this process smoother. So there are a couple of reasons for why quantum computing is hard. So first is that it's relatively young field. So it's mostly academic. Well, it's like, you know, the industry really started getting some traction just a couple of years ago. Another reason is that we have very like crude abstractions, like very, say, we've been, you know, teaching quantum computing for only, I don't know, 30 years, perhaps 40, maybe. So we just are not good at teaching quantum computing yet, even though the abstractions, even though like the concepts are not necessarily super hard, we don't have enough experience. So a couple of years ago, I met Nathan Wiebe from Microsoft, great researcher, at a conference, and he was doing a tutorial about Grover algorithm. And we chatted a little bit afterwards. And I said, you know, this is like third or fourth time I'm learning about Grover's algorithm. And like, I finally started to understand what's going on, but probably I still don't understand half of that. And we talked about like teaching quantum computing, and he said that he recently read Principia Mathematica by Isaac Newton. And it turns out that the way Newton was describing calculus, it was, you know, super complicated, and that simply throughout the last 400 years, we learned how to teach calculus, how to explain it. And well, with quantum computing, we're still in very early years. So that's something. Another reason is that because it's a young field, there are relatively little educational resources beyond introductory level. So I would say that for, what gates are, Hadamard gate, qubit, entanglement, superposition, or like this basic stuff, you have pretty decent books, pretty decent tutorials. But if you would like to go a little bit further to more, applied quantum computing, more NISC quantum computing, then there's simply, they're just papers, right? So there's little middle ground between basic tutorials and scientific papers. And well, it's just making it harder to learn. Okay, another thing is that the field itself is just enormous. I mean, if you go into quantum computing, you can work on quantum computation, quantum cryptography. There are like different aspects of hardware, of control systems, error correction. You can work on like physics experiments related to quantum computing, or you can work on error correction codes, on software at different layers of abstractions, compilation. So it's very interdisciplinary, but it's so broad that sometimes if you just like enter the space from the wrong place, you kind of get distorted view of it. And sometimes like some people talk about it in certain basically the same things. Some subgroups in this area talk in different way. So that also might be confusing. I personally had it a couple of times that I was reading something and then reading about the same thing in different place, and they were using a very different language to describe basically the same thing. Okay, and the last reason is that there is a lot of hype, and this means that people often write low quality articles, low quality tutorials, learning materials in general about quantum computing, because they want to be popular, or for whatever reasons they are like riding this hype wave. And it means that even though they are not qualified to do so, and they are just like replicating some mistakes, some misconceptions that they read about in like some other articles. And well, it's just like super easy to find something like this on the internet. If you just do a quick Google search, well, it's easy to just learn something wrong. And also, because there is a lot of hype, I sometimes get people ask me, hey, so how can I use quantum computing in my day-to-day work? And I say, it's like the technology is at so early stage that you can't use it in your day-to-day work because there are no applications for quantum computing. And like right now, maybe in 10 years there will be something that you, for example, as a data scientist, machine learning engineer, you will be able to do that, but like not today. So yeah, that's like why like hype doesn't help a lot here. Oh, there's like one other thing I want to say. So where do I get my data from about, I sometimes say, a lot of people say something, or there is a common misconception. So basically, now I'm running this quantum mentorship program. Before that at BOR, I was also running a similar program. So I had opportunity to like work with people and see what they struggle with. And also a lot of people write to me either emails or at LinkedIn, asking me some questions. So, and also I just tend to, just like casually talk with people on various occasions. So that's like, why I think, it's not like from 2 or 3 conversations I had in my life. It's more like tens or hundreds of conversations, either live or online. Okay, so now okay, so there are some also like some common pitfalls where you start doing quantum computing. So one is, some people think that they need to get access to the real hardware in order to start doing quantum computing, which is totally not true. You can do real research, real science, and real engineering with just using quantum simulators. I personally, I was running some stuff on D-Wave, but regarding gate-based quantum computing, I was running some demos on IBM's machines, and basically that's it. Like all of my work is done on a simulator. So yeah. Another thing is that a lot of people say that, well, I need to understand quantum mechanics first before I get into quantum computing. Not true. I will, talk about it more later. I mean, it helps definitely, but it's not a hard requirement. Also, many people, because of this lack of educational materials, I mentioned earlier, some people think that Shor's and Grover's algorithms are the most important algorithm in the field, and they spend a lot of time trying to master these. And while there is nothing wrong with that in general, it doesn't align well with their goal sometimes, because you can just learn much more, much faster by learning some other methods that are commonly used, like VQE or QAA. And also, the last pitfall, I think that people, beginners, tend to spend a lot of time on, which is just a waste, is that sometimes people ask me, hey, have you heard about this new breakthrough? So they designed this new type of qubits. What do you think about it? And I see that there are a lot of articles about this or that breakthrough, and honestly, well, I'm not a hardware specialist, so I cannot really, I don't know what to think about this new type of hardware. And I don't think, most of the time, it's not super important for my day-to-day life. And I'm just, reading all the articles that I cannot really judge whether they are just riding on a hype wave or whether they're actually valuable. If I read all the articles, that I would waste a lot of time. So I would rather just sit down and read a scientific paper, or read Nielsen and Twang and learn a little bit more about quantum computing, rather than read all those news articles, because in the end, some of them have a lot of value, some of them don't, and it depends also on what you're trying to achieve. Okay, so now let's go to the second part, which is how to learn quantum computing. So I will start from assuming you don't know too much about quantum computing, so that you're a total beginner. But as I said, I hope this will apply to those of you who went through the beginning as well. I'm just checking the Slack. Okay. I hope everything is okay still. You can hear me and you are there. I just want to say that making a presentation on Zoom without being able to see whether you see me or whether you're sleeping or listening or seeing your reaction is super weird. So I hope everything is good. Okay, how to learn? Oh, someone wrote something. We're listening. Oh, cool. Thank you. Happy about it. So that's good. Good. Thank you. Thank you. Awesome. How to learn quantum computing. So here, this is a little framework I created. Well, that's not something, very scientifically sound. It's not that I did years of research on how you should learn quantum computing, and this is the best way to do that. It's just a way of organizing, this process. So first, specify your goal, then find some resources that will be useful for learning, then learn a lot, get good foundations, do some hands-on learning, and discuss it with others. So I would like to say that this process would be linear in the sense that, you know, you start, you go to the last point, you discuss what you learned with others, then you kind of reevaluate what is my goal now, what do I like to learn now. But in reality, this is more like, you know, the thing on the right hand, that it's super messy, it's non-linear as hell, and so you often just like skip some steps and spend a lot of time on other steps. Well, you know, learning is, you know, creative process, I would say. It's messy, so just be aware that this is just like general framework, like fit it to yourself, right? So the first step, which is pretty important, and I think a lot of people kind of don't really take moments to reflect on what are their goals, is specify, like, answer a couple of questions like this. So why do you want to learn quantum computing? Do you want to learn quantum computing because you heard about it and you think this topic is interesting, or because this sounds like a good marriage of computer science and physics, and that's the reason why it's exciting? Or are you just like a technology geek who would like to, you know recent trends? Or do you want to land a job in quantum computing? Or do you want to do PhD in quantum computing and focus on academic research? So depending on, like, you know, how you answer this question, you should approach learning like in different ways. So another, which is somewhat connected, is like, how well do you want to understand it? Because, you know, if you just want to have a general field overview, that's like something different than, you know, having a mastery over quantum computing. And understanding the basics and having good foundations is different from knowing what could be possible applications and, you know, what's the state of contemporary quantum computing. So, you know, it's good to know this. Another is like, it's good to think like, what's the most interesting part about quantum computing? So for me, from the beginning, the most interesting part was applications, like real world applications. So I focused on this part. But for some people, it's, you know, the beautiful math behind it, or just like, you know, how can you kind of join physics and computation and like information theory? So, well, that's good to know, you know, what's that part. Also, another thing is, it's good to know like what background knowledge are you missing. So perhaps, like, I'll say that if you identify up front that, well, you are not that good in linear algebra, and that's probably, it would be wise to first spend a couple of weeks, you know, refreshing your linear algebra and maybe then go into quantum computing. It might be much more effective than just like going straight into quantum computing and then having to, you know, bear with all the matrices, tensors, and whatsoever, Hilbert spaces. And the last thing is, sometimes for some people, there's like some obvious starting place. And it like, just like the learning process will be much, much easier if you start from a domain that's similar to, you know, that you already know. So for example, if you have a huge interest in cryptography, then perhaps, even though you might be most interested in quantum machine learning, perhaps you should start first with quantum cryptography, because a lot of concepts will be familiar to you. So you will have like smaller shock trying to understand some concepts. So yeah, it's just a piece of advice here. So for example, for me, I started from optimization, and I tried to focus on optimization problems first. And yeah, that I think that helped. Cool. Second step. It double clicks every time. I have no idea why. Resources. So there are, when you start looking for resources for learning, it's also good to know, like, first, you know, what's your style? In the sense that if you go to a Slack and ask, hey people, what are good materials about quantum computing, people will tell you what they like, and it's not necessarily something that you would like. So it's good to know upfront, like reflect a little bit on whether you like to read textbooks or whether you prefer to do like hands-on code tutorials, or whether you just like heavy math or rather more hand-wavy type of math without that much details. So yeah, like some books, you know, are more this, some are more that. It's good to know. Another thing is like don't. So let's say you choose Nielsen and Chuang as your primary learning resource, which is an excellent choice, and you read something and you're stuck. So then just try to go to another book and try another resource, or find a, I don't know, a video on YouTube about it. Because, you know, often some authors, well, they are just humans, right? And they are better at some things, and they're better at explaining certain concepts, and they maybe are not that good at explaining others, because that's, you know, not necessarily the area of expertise or whatever. So just like for that reason, it's sometimes good to just check the same topic in a couple of books. Oh, something happened here. Sorry. Go back. Sorry, like, guys, I hear nothing is the same for you. So is everything okay? Can you? Okay, great. Okay, awesome. So sorry, it's just like popped on my screen suddenly. Good. So back to the topic. So yeah, it's just like, you know, pretty useful to have a couple of good sources so you can compare. I personally like did that a couple of times. So I was, when I was writing like about the article about VQE, I couldn't, you know, understand some concepts. I was trying Nielsen and Chuang and reading it a couple of times, and it didn't help at all. And then a friend told me about another book, and well, that was just like super well explained. So it was super easy for me, and I just got it in a couple of minutes. Avoid quick and easy articles. So yeah, as I said, you know, if you struggle with understanding a concept, and there is article like, and you spend, you know, significant amount of time, like hour or 5 hours, trying to understand what the hell this is about, and then you try looking for answers in the internet, and you find a Medium article which is 3 minutes long, which is about what you are trying to understand, that perhaps this article is just like not very good in quality. I mean, perhaps it's excellent. Perhaps it's written by a specialist who really understand this topic, or a person like you who just like got over this moment in their life and they understood it and wanted to share like an, you know, comprehensible explanation for given problem. But there is a good chance it's just, you know, someone trying to explain it, but really twisting the idea and explaining it wrongly. And yeah, you have to be careful about it, and just like avoid this kind of articles. If you read them, it's like have this filter in your head that like the person that was writing this is not necessarily, you know, understanding it really deeply. I don't want to sound negative. I mean, there are a lot of really good resources, and like I've read articles that were not 100% mathematically accurate, but helped me really, you know, get some intuition about the topic. But it's you know, don't just be careful with that. And also another thing is that one of the resources, as I said, is reading scientific papers. And if you go beyond any basics, you will probably just face, hey, I have to read scientific papers in order to understand something. So this is the issue. And the problem is, I mean, I like scientific papers a little bit, but the problem is that reading scientific papers is like a separate skill. It's just like, I don't know, if you are a software engineer, you just might have never opportunity to learn how to read scientific papers. If you were studying physics, as I did, I had opportunity to learn it a little bit, and then I kind of got better at it. But I guess at this point in this area where we are, it's just, if you just want to get deeper, you just will have to read scientific papers, and there's no way around it. So I'm sorry about it, but just try not to get too discouraged, and try to try it once, try it second time. Don't read the whole article up front. Maybe read the introduction, the abstract, the conclusions. Come back after a month when you have better understanding of the topic. Try again. Yeah, don't get too discouraged. That's everyone has problems with reading our scientific articles, like even scientists. Some are just like not written particularly well, and some are written beautifully well. That's life. Okay, a couple of good resources that I like. So Nielsen and Chuang, that's like classic textbook for quantum computing, probably the best in existence. Probably the best place to start. Yeah, that's it. Quantum Country, this is an interactive essay written by Michael Nielsen, the same as one from the book, and Andy Matuszak, I think. This is brilliant. This is like the best intro to quantum computing I've seen, and I'm recommending it to everyone that asks me about some resources to start. It's like Quantum Country is like, should be like the default, starting point. Like everyone, when you write quantum computing in Google or other search engine, the Quantum Country, like I want to learn quantum computing, Quantum Country should be like the first 10 results in your search, because that's so good. After doing quantum computing for 1.5 years, I read that, and well, I just learned so much. Another pretty good is Scott Aronson's lecture notes. Yeah, that's pretty decent source. Also, Scott Aronson's blog is good if you want to get a better idea of some recent breakthroughs in quantum computing. So for example, when Google announced the quantum supremacy, he had very comprehensive article about what does it all mean. Quantum Open Source Foundation has quite a lot of resources on their site, so you can just like go through the list and see what's there. And well, of course, my blog, I think it's also a good resource. People tell me they like it, and it's helpful. So yeah, I also recommend this. There are like many more good places to start. It's just like I know a couple of these in particular. So I recommend this. It doesn't mean that others are not as good. It's just like, my personal perspective on this. Double click. Okay. No, the sources are not in preferred order. It's just like, some order. Actually, like QOSF list here is just like a list of resources. So you can just like browse stuff that's there. Okay, get good foundations. So as I said, it depends on your goal. If you want to get a general overview of the field, then probably you don't need to go as deep into basics. But in general, I think many people just like kind of skip over this step and don't treat it seriously. And well, I definitely did not. So I mean, I definitely skipped here, and it came back to me many times that basically, like, there are some concepts from quantum mechanics that I learned on university, and I simply didn't remember well enough, and I forgot about some details, and then it got back to me. So I should actually first recap some of the knowledge that I already like had, and go back and like relearn it before I go deeper. So yeah, this is a mistake that I did. So that's why I'm telling you, well, get the basics right first. So I created this small table. It's again super subjective. Probably any other person in the field will create a different one for you. But I divided in 3 columns. So essentials are like things that I don't think you can learn without having these skills. So linear algebra, yeah, you just need to understand it. I mean, it will just make your life so much better, even beyond quantum computing. Just linear algebra is like, I think, one of the most important topics that I've ever learned. Good resources on that. So on Khan Academy, if you don't know it at all, on Khan Academy, there are good intros to that. Free Blue One Brown has excellent YouTube videos about linear algebra, and in general, he has like excellent videos. And also on Fast AI, there's a course on linear algebra, so you can check this out. Then basic quantum mechanics. So by basic, I mean you should know the postulates of quantum mechanics. You should know why, you know, what's the collapse of the state, and you should know what's the Dirac notation, and it will just make your life easier. But I guess this is just like first 2 or 3 chapters from any quantum mechanics textbook. And you can definitely go pretty far with just this basic knowledge. Basic quantum computing. Oh yeah, I mean, it's not that in order to learn quantum computing, you need to know basic quantum computing, but in order to, this is essential to know the basics well. So by the basics, I mean, whatever there is in quantum country essay, because they cover basically most of that, like entanglement, what are circuits, what are measurements, superposition, Hadamard gates, different other gates, and so on and so on. Yeah, I will post some. I don't have all the links here, but I will add them also afterward to this presentation, and I will post this presentation on Twitter and LinkedIn, and yeah, so just letting you know, don't be too stressed if you don't hear something. And basic Python. So while you can just go with math and you can just kind of do pen and pencil, I really believe knowing basic Python is like extremely useful, and it's like essential to do something like in quantum computing. If you know other languages, yeah, that's cool. Python is pretty easy, so you'll be able to do something with Python pretty quickly. Okay, some stuff that I found pretty useful. It depends on like what topics are you particularly interested in, but when it comes to variational quantum algorithms, so the stuff that I'm mostly interested about, optimization, like gradient descent, and I don't know, like discrete optimization, and other stuff like from, well, methods like mathematical optimization. It's super useful. I mean, it just, yeah, I just like use it on my daily basis, this knowledge. Machine learning. So while you not, even if you don't go into like quantum machine learning, some concepts from machine learning are really useful. Like the way, just like intuition about linear algebra, about like multidimensional vector spaces that you can get by doing machine learning is pretty useful. Well, the skill of reading papers, as I already mentioned, yeah, like this skill is pretty good. I don't think there is a good way to like practice it other than like reading papers that are of interest for you, but yeah, like just put it there. Good programming skills. So the more you want to go into software, the better programmer you are, the easier, you know, the less time you will spend on figuring out why your code doesn't work because there is a missing colon or indent or whatever stupid reason there is, and more time you can spend on actually the core and the science behind it. And also, I think that having a field overview is pretty useful in general. I mean, what are different companies there? What are different paradigms? What are different applications, potential applications, and so on? It gives you just like more context. And there are like some situational things. So really depending on what you want to do, what you want to learn exactly. Advanced quantum mechanics. Yeah, I put it here more to illustrate the fact that you don't need that in general. I had 1 year of quantum mechanics, and that's like definitely enough for me to do what I do. I honestly don't use probably half of the stuff that I was learning at my university. So yeah, like you don't need to have PhD in that to do quantum computing. Git, I wanted to put Git into essentials. I didn't, only for one reason, which is because if you don't necessarily want to work on a software project, then perhaps you don't need Git. But Git is like the best tool I've ever used, like software tool. Like it saved me so many times. If you don't know Git, just like go and learn it. And if there's one thing, if you are doing software and there's one thing you can, take from this talk, is like learn Git, and it will, whatever you do, whatever are your interests, it will just, if you code, it will make your life 100 times better. So, and domain knowledge, again, it helps, but you don't necessarily need to be, I don't know, expert in cryptography to learn quantum computing and to understand how quantum cryptography works. Though if you want to get all the details right, it definitely helps. Yep, so, okay, checking the chat. Yeah, hands-on learning. So the fourth step, and yeah, actually these two probably should be mixed up. I mean, I like to kind of read something, then like code an example, then read it again, then try it in code. It just gives me more intuition. But here, by this part, I actually mean more like doing a project. So I really recommend just like taking an interesting problem to solve, interesting like project to work on. For me, it was, hey, can you solve traveling salesman problem with quantum computers? And that was like a good place to start, because it's like concrete. It kind of guides you what do you want to do. And even though it's not necessarily 100% useful, and you'll probably do a project which is like nothing groundbreaking, or perhaps even you might be wrong. By working on something concrete, it will like force you to learn stuff that is in general useful, right? Not go into areas of like theory that might not be really interesting, like not practical in some sense, but rather focus on stuff that help you solve concrete problems. Okay, choose interesting project, then take it easy, in the sense that, yeah, this is hard. I mean, I was mentoring on one project where we tried to solve job shop scheduling problem, which is a combinatorial optimization problem. And even though I thought it's like similar to traveling salesman, it turned out that it's much harder. And well, we like that project failed, unfortunately. We didn't get like too far with that. And yeah, that's like the risk. I mean, upfront, it's hard to say how hard the project will be, even though there are like two problems that seem similar. If you get into details, one might be super hard and the other might be not that hard. So don't get frustrated if it doesn't work. Well, try again, maybe change the project, take it easy. Okay, choice of framework doesn't really matter. In most cases, if you just want to start, well, you can use Python, you can use Qiskit, you can use Circ. Some of these are better for some stuff. Some of these are worse. Some are better, libraries, better maintained, have better community. Some don't. But in the end, for starters, it doesn't matter. I mean, people sometimes ask me, hey, which one I should use? Like, whichever you like. Maybe Q# is a little bit different because it's not like Python. But if you know C#, then Q# is probably the one of your preference. But for the basic stuff, you can more or less do all the same things. In all of those frameworks, it's just for more advanced, they are sure there are differences, but don't worry about it in the beginning. But be careful with different paradigms. So there are different ways you can do quantum computing. So there's this gate-based quantum computings. So like circuits, like Hadamard gates, Pauli gates, and so on and so on. But there is quantum annealing, which is pretty different. There is D-Wave is the most prominent player here. There is how it's called, continuous variable quantum computing, which Xanadu is pioneering, a company from Toronto, which is totally much more difficult than like gate-based quantum computing, even though actually their approach is also gate-based. So it might be confusing, but just like make sure you are learning the right thing, because I've met some people that like they learned about Xanadu, for example, and they started from continuous variable quantum computing, and they got pretty confused because it's different from like regular qubits and gates and so on, and it was hard for them to actually understand why they are so confused. Okay, and then, well, while there is great community for quantum computing and great support on different Slack channels or Facebook groups, like please first read the docs and then ask questions. Like don't waste people time on asking questions that are on first page of getting started in given project. It's just like not being nice to people. So I have there's this nice rule that if you cannot, so it works well when you work in a team, so that you all are working towards the same goal and you don't want to waste each other's time, but at the same time you don't want to get stuck, because it's also like wasting team's time. So if you do something for 30 minutes and you cannot solve your problem, then you ask someone else. And that's like a good rule of thumb in general. And I think here also, like, don't just bother people with your questions if you spend just 2 minutes thinking about how to solve this. And I actually wrote a whole article about how to approach starting your first quantum computing project. It's on my blog, so yeah, you can like read some more, a little bit more there. I'm looking at time and it's not looking particularly well, so sorry if I run, if it gets long. Organizers, please tell me if there's like some hard limit on. I mean, that's.
No, I think you're doing great.
Okay.
The thing is that if people are busy, they can just leave the meeting. That's one good thing for these meetings, without making noise.
Mm-hmm.
Thanks. Yeah.
Okay. I mean, it should be like half an hour more or so, but just heads up. Okay, another thing, I think this is crucial, and this is something people overlook, and I learned it a little bit the hard way, that it's really important not to be alone in this learning process, and just like try to find some people of similar interests. I don't know, at your university, at your job, at your like local city. Maybe there are meetups now. Everything is online, so also like online, it's a good place. Join Facebook groups, quantum Twitter. So like follow some quantum people on Twitter. There are different Slack channels, Stack Overflow. I don't have like any particular place that I can recommend to you. But yeah, definitely. I mean, there are like small communities that work together, that meet from time to time, just, I don't know, read books together and try to figure out what it's all about. And it's just like much more efficient if, you know, you can talk with others about what you're learning. So definitely, like, don't be shy here, right? Ask questions. So don't be afraid of asking questions, even if they're like basic and stupid. If you know, because I made the point about like not asking kind of trivial questions before, but if you really struggle to understand something, you might struggle for another couple of hours as well, and it's just waste of your time. And I mean, sometimes it's not. Sometimes you will figure it out and you will learn a lot. But sometimes it's just worth, you know, asking on a Facebook group or on a Slack, hey, you know, can someone explain this or that to me? If no one responds, well, that's too bad. But if someone does, it's just, you know, better for everyone. Don't feel bad. I think this is pretty important. So like, everyone has to start somewhere, and the fact that you don't understand all the details, yeah, I mean, why should you understand all the details? I mean, experts in the field, like professors, you know, they don't understand all the details. That there are like areas where they have great intuition, great understanding. There are areas where, well, they have some, you know, they lack some knowledge, right? And that's, you know, the field is too big to like be an expert in everything. So don't feel bad that you can't understand something. Just, you know, be polite, be nice to others. Don't demand, hey, I'm here, I'm asking question, why no one is answering it? You know, be patient, be just be nice, right? I mean, I live in Canada, like people are nice here, right? So I think it's a good thing. Yeah, another. So I would say there are like a lot of questions in quantum computing that are without answers. So, you know, people that are really at the frontier of science, they don't have all the answers. This is a very active area of research, and sometimes, you know, people who are just starting are asking questions that like just no one on this planet knows how to answer. And it's important. I think it's important to get this perspective, especially for people with like lower, I don't know, like self-esteem, self-confidence, that are afraid to ask. And yeah, I mean, that just, you know, no one's perfect. That's the way it is. Remember about it. Don't feel bad. Okay. Career development. Yay. So that was the end of section learning. Now I would like to tell you a little bit about how do I get a job in quantum computing? How you do that, right? Where to start? So I'll just drink some water. Give me a moment. Okay, people, I'm back. So career development. Relevant blog post is like how I got the job in quantum computing, which is on my blog, with my story and some tips. So you can read that afterwards. I would say that you know, here again, like this is based mostly on my experience, my observations. I have not done research on this topic. I have not done, you know, interviews with people in the field, which gives you the real answers. So, you know, I might be wrong, but these are my observations. So the job market for quantum computing is very small and very young. So this has a couple of consequences. So first, there are little resources when it comes to looking for a job. In the sense, if you are a software developer and you want to find a job, there are like a lot of websites where you can look for jobs, look for offers, compare, I don't know, salaries, learn about different companies, about, you know, like interview processes for specific positions. Here, well, there are not that many. I not even know if there are just a few. So that makes it a little bit harder. The second thing is that, you know, the field is small, and this means that there's this, like, I don't know, like theory or, you know, of little world that you can connect with any other person on earth in like 7 steps. So, you know someone that knows someone that knows someone that blah, blah, blah gets to that person. At most 7 steps. And in quantum computing, it looks like this is 2 steps. Like, probably not true, but it's surprisingly often like, oh yeah, someone talks about something. Oh yeah, I know this guy. Like, it's just the world is that, you know, the world is small, and therefore it's like pretty easy to get to some people through your network. And also it means that, you know, reputation is pretty important, because you cannot like hide. I mean, if you have bad reputation with someone, then probably like other people will know. So you have to be careful. Okay, and like the companies are extremely dispersed, like geographically. So when I was doing research, and so there were like 10 job offers that I could apply for. 20 perhaps in general that like I was interested in, but like out of this 20, like 10 required you know, PhD and 5+ years of experience, so they were pretty yeah, like out of my reach. So most of companies back then were based in either Toronto, Bay Area, or London. Right now, it grew like throughout those 2 years. It grew like a lot. Like I don't have statistics, but like the growth is really, really big. And while this is true, and there are many more like opportunities, still the issue is that there might simply not be a quantum computing company in your town or in your country even. And yeah, I mean, it might turn out that you need to relocate in order to get a job in quantum computing. And if this is something that you don't want to do, then you can try to look for remote positions, but I'm not sure how it works. It also might be tricky. So yeah, that's the way it is. And another thing is that a lot of things on chat, so I will just like check if I can. Come on, Zoom, come on. Oh, here it is. Oh yeah, I will talk about some of the stuff you were asking later. So the field itself is vast. I mean, you know, as I said, there are like a lot of like subdomains here, and we need people with a lot different type of skills. And this is good on one hand and bad on the other. So the good thing is that if you are, I don't know, like expert in operational research, there might be a job that some company might be looking for someone with your expertise. And you don't need to know quantum computing very well to get that job, because they're looking for skills in operational research, not in quantum computing, because, you know, they're a quantum company, they already have a lot of quantum people. So this might be a chance for you. But on the other hand, there are not that many opportunities like this. And well, it might turn out that there will be just like one job offer that is for your skill set exactly a year or every couple of months. So you need to like have very good like the better market research you do, that like the better for you. I mean, that's true in general, but in here it's really opportunity, like window of opportunity might change pretty quickly and might close pretty quickly. And this also means that you don't necessarily need a PhD, because there are a lot of, you know, at Zapata, we are not only scientists, there are a lot of, you know, software engineers, for example, and we need them. to build, the infrastructure for our product. And these are not necessarily people with big background in quantum computing, right? So sure, they are learning now, and like some of them are like, yeah, but some of them didn't have like a lot of, knowledge about quantum computing. And they don't need that much because they are doing software engineering and not science. So quantum computing companies are not all about, doing science. There are other stuff like, I don't know, product development or graphic design, and there are different skills that might be useful for different companies. So, okay, and the last thing is there is a lot of hype. So even if you find, I don't know, startup that has quantum in name, it doesn't really mean that the core of their business is quantum. And the problem is that not all of these companies are 100% honest about it. So some people, like there are startups that claim they are doing quantum computing. In reality, they are not doing a lot of quantum computing. So if you get there, you will actually not learn much about quantum computing. So yeah, just like be careful here and do your research first. Usually you are able to tell that if you do your research. Okay, and so now like a couple of tips how to approach getting a job in quantum computing. So I divided in like there are a couple of things that you want to do, and there are a couple of ways to achieve that, which doesn't map in an easy way in some cases. So yeah, that's why I did it like this. So things you want to do. You want to build your reputation. As I said, the field is small. If there is any way you can, start being recognizable, not being like a random person interested in quantum computing, then it works well for you. Either through, I don't know, like doing videos, writing articles, contributing to open source projects, whatever, networking with people, attending conferences, different ways, right? Build your network. Yeah, the more people you know, the better. I mean, that's obvious, I think. Build your portfolio. Just it's all about signaling. If you have a project that shows that you understand a certain, I don't know, algorithm, or you have expertise in certain technology, it's better to be able to show that to people than not having that, right? And also, as I said, you need to have good understanding of the job market. That the more you know, the better for you. Okay, so how to achieve this? So first is contributing to the community. I wrote again like an article about this. You can read that in more details, but there are like a lot of ways you can do that, either by like contributing to open source projects, or helping, I mean, organizing some local meetups, or well, many others. If you are in academia, writing high quality papers is always a good idea. I mean, it's obvious, sure. And if you are not in academia, it's probably hard to do, but yeah, it's a good idea to do, like good thing to do. Start your own projects. As I said, it's great learning opportunity, but that's signaling, right? So when I was trying to get to Zapata, I decided, well, how will I show to this company that I am able to do the job, that I am like good quantum software engineer? So what I did, I decided, okay, I will take a paper written by them, which was VQF, variational quantum factoring, and I will reproduce the results from the paper. And I did that, right? I spent about 100 hours doing this project, and I reproduced the algorithm they presented in the paper. And I basically showed them, hey, people, I can take a paper and translate this paper into code. And I don't know if, that was super important in the recruitment process, or that was just nice bonus, but it worked. I mean, I got the job finally. So doing projects is, definitely good idea. Go to conferences, events, meetups, whatever, meet people, talk to people, worth it. Definitely. Start applying now. So even if you don't feel confident about your skills and you think that, the chances that you will get the job are like super low, Just do it and try, and you will learn how the process looks like. You will, if you get to the interview, you will see what kind of questions people are asking. You will meet those people during the interview, and this is, well, you meet people this way, right? I mean, this is one of, you establish some relationship with them. You might get some feedback regarding, like, for example, hey, you did a great job on this and that, but really we need a person that has more, I don't know, hands-on experience with machine learning. So, that's good feedback on, like, what should you do next. So don't be afraid. If you fail, well, you'll just waste some time on the recruitment process, but stuff that you learn might totally be worth it. Do your homework. So if you apply to a company, just, see what the company is about, who is working there, have they published any code or papers recently, just like show, first you will know better what this company is about, and second, you will be able to talk with, like, you'll be able to show to your recruiter that you actually care. And lastly, talk to people. When I was looking for like my job first time, I was trying to get into quantum computing, I was just cold mailing people and saying, hey, I'm Michael and I would like to move to Toronto soon, and I'm looking for opportunities in quantum computing, and do you have 30 minutes to talk? Maybe you need someone like me, maybe not, maybe you can help me, maybe I can help you, let's talk. And yeah, I mean, I think it worked. I mean, I met a lot of people. I am in good relationship with some of them until this day. Well, a lot of people just have not answered my email, or nothing really happened. But I think it's still worth trying, right? Like, the worst thing is that they won't answer, right? Okay. And okay, so I'm almost at the end. So key takeaways from, like, this whole presentation is: answer why. Why do you want to do this? Why do you want to learn? What's your goal? That's just, like, good thing to do. Learn from the best, not from the mediocre. Try to find the best resources. It will save you a lot of time and confusion. Don't cut corners. Do your homework, whether you want to get a job, whether you want to just learn good, science. Like, spend some time. I mean, it all requires hard time and hard work. And I spent a lot of hours trying to get where I am, working hard. Get your hands dirty. Hands-on experience is really, really important and really valuable. So, yeah, definitely try. Even if your project will be a huge failure, still just try. And don't be alone. Find people, join forums, Slack, Stack Overflow, whatever, and meet other people and talk with them about your interests. So finally, that's the end of the talk. And they're, like, just small little thing. Some stuff that I was not talking about but might be useful for you is Unitary Fund is a great place to get funding for your projects and to actually check out what projects people did. I took part in Unitary Fund. Amazing experience. 80,000 hours is, like, this has nothing to do with the quantum computing, but this is, like, best career advice website in the internet. Not only, like, much more than this, but most of the stuff I learned about career development was from 80,000 hours. Fast AI is, oh my God, I mean, it's just, like, the single best deep learning or machine learning probably course I've ever seen. So if you want to learn ML, yeah, just go there. It's incredible. And Quantum versus Open Source Foundation, I already mentioned. There are a lot of good resources there, so you can check it out. Where you can find me if you are interested? Come on! If you are interested in finding me online, you can send me an email. You can find me on Twitter. I have a blog, Musty Thoughts. I already mentioned it a couple of times. You can find me on LinkedIn. You can find some of my projects on GitHub. Yeah, like, in general, if you want to contact me, email is the best way to do that. Because I might not answer you in like a week or two, but I will finally get there and answer you. So yeah, so that's it. I will post, as I said, I will post the slides on Twitter and LinkedIn, I guess. So you'll have access to this. And if you have any feedback regarding this presentation, if you liked it, if you didn't like it, please tell me why. Please tell me not only that you liked it, but also what was the most important and what was the least important stuff. Because the next time I will be making similar presentation, it will just get better. Okay, so thank you very much. And I will try to check out some questions. Okay. Please mute and you can ask questions in chat. I will read them in chat. I hear someone has or something. Please mute. Okay, I think I
Can
have.
you recommend to mute everyone, and then people who would like to speak, they can raise their hand?
I think you can just unmute yourself directly after everyone's muted. So that's probably a good way to do it.
Yeah, that's another option. And probably turn on your camera too when you're asking your questions.
Okay. Question for you. During your useful foundation part, you talked about optimization and you mentioned two areas. I'm wondering if you could go into a little more detail about that, maybe with discrete optimization, what an example of that would be, or if you could just expand on that a bit more. Thank you.
Michael, did you hear the question?
Oh, he's on mute.
Sorry.
Okay.
I forgot to unmute myself. So yeah. Okay, so I heard the question, and I would say I would try to give some concrete examples, but in general, like for me, I feel this is more about like just the general intuition and understanding how this type of things work, rather than like something super specific that I used. But especially for variational quantum algorithms, there is this optimization step which uses classical optimizer, and knowing how the optimization works, what are some common issues. For example, if you want to restrict the optimization space, how do you do that? How you make your optimizer, not go into places that you don't want it to go? It might be useful. Gradient descent, like I said, useful methods. Not very like important to understand it. Also, there are all kind of non-gradient based optimization methods that might also be good to learn and have like some basic understanding of what's the difference between them. Some other thing that, yeah, it's pretty vague. I agree, but understanding, because in quantum computing, the trick is that evaluating the cost function in your optimization process is pretty costly because it requires you to run it on the quantum hardware, and that's like a bottleneck. So, understanding why given optimization method might be better because for quantum computers, because it requires, less calls to the quantum computer itself, it's good to have like some idea of, what are the trade-offs in optimization, for example. Yeah, I would like to be able to say something more specific, but.
No, that's helpful. I was just wanting to a little bit more expanded. Obviously, that could be a talk in itself. So, thank you.
No problem.
So I have one question. So the companies, quantum companies, each one is working on silos, like individual areas. So it is another space. We have a space station, which is collaborative effort by different companies working together. But in quantum, everybody is working on their own angle. So it is very slow progress. I mean, it is not showing anything past decades. So anything in a scale where the space station, like where they can collaborate and do that, will be helpful, I feel. Is there anything activities on that collaborative effort is done between quantum computing companies?
I mean, like, I'm not aware of everything that's happening in the space, but yeah, like a lot of companies are working together because, you know, there are different layers of the stack, right? So there are some companies that are focused on creating better hardware. There are some that are focused on creating better control electronics for these systems. There are others that are focused on creating software tools, others that are focused on creating algorithms that can run on the hardware, and they have to work together in order to, you know, get something done. So yeah, like there is a lot of collaboration. I would say that, like, I feel that this field is very collaborative, and of course you have competition as well, but competition is usually kind of more obvious between companies that are trying, you know, are at the same level. So let's say you have two companies that design compilers for quantum computers, then yeah, they obviously won't be that willing to, you know, collaborate with each other, but they both will be super happy to collaborate with hardware companies or algorithm focused companies or something else. So I think it's pretty collaborative. I'm not sure about like huge centrally coordinated initiatives, like, I don't know, national level or smaller level, but this is just like my lack of kind of knowledge in that area. I won't say that there aren't any.
Thank you.
I've got a couple of questions, related questions, if that's okay. So one of them was, is there like a good website that you know of that has a list of, you know, good projects for, I guess, educational purposes that somebody can work on? And
Quantum Open Source Foundation, I would say.
Okay. And then,
yeah.
What do you think is like a really good online quantum computing course?
So so the only one that I did, yeah, so one of the reasons I wasn't talking about courses is because, well, I don't have much experience for quantum computing, but one I did was about quantum machine learning by Peter Vitek, though I'm not sure whether this course is still online. I mean, it was great. It was more advanced. It wasn't for like beginners, but you can try to find it. If you actually find a working version, please send me a link. I'll be happy to see that. But also there are others that I've heard from people that are good. Is MIT. I think this one is paid, but there's like this huge course from MIT that a lot of people praised. As I see, Third France just sent in the chat this course on FutureLearn. I also have not like done this myself, but I've heard also good words about this one. Yeah, so these are the ones that I like. I've heard people say they are good, but I'm afraid I cannot really recommend something else.
Thanks so much. Thank you.
Hi, Michael. This is Amit. Thanks for your talk. Give a good understanding about where to start for beginners like me. I would like to understand what kind of applications do you see of quantum computers in near future, what industry it might really help, and where do you see the future of quantum computing going further? If you can just throw some light on it.
So, well, with huge disclaimer that it is just speculation from my end. I don't have experience and knowledge required to answer this question with any degree of certainty, because I just don't have, you know, I'm doing software and algorithms. I don't know that much about hardware and other things. And with that being said, I think, well, chemistry simulations, machine learning, optimization are kind of standard things that a lot of people talk about, which in turn are applicable to like a lot of different industries and problems. So material science perhaps as well. And I guess I would say in the next couple of years, we'll see some practical applications, but probably still in the, like, not, you know, fully, like full-scale production environments, rather some first pilots, prototypes. But I mean, I know this answer is very vague, but honestly, like, no one knows. I mean, really, it might turn out that there is someone in some startup in the stealth mode that, you know, are working on some breakthrough that will go live next month, and, you know, these predictions will be totally worthless. Or there might turn out that there is some fundamental reason why this is much harder that we didn't know before, and it will delay everything. So yeah, hard to say. Many different industries, machine learning, optimization, chemistry, simulations, but that's it.
Yeah, thank you.
Hi, Michael, can you hear me?
Yes, though you are a little bit quiet.
Sorry, I'm going to speak a bit louder. Thank you very much for the presentation. It's very much appreciative. I would like to find out, wouldn't your company be able to have an online resource where us students, I'm a student in applied maths and the physics stream, working on valence bond and orbital, the molecular orbital theory for chemistry using quantum computers, so that we can submit documents or algorithms or white papers or whatever the case may be, so that we can get feedback from you guys who have, you know, direct access to companies like IBM and give us feedback. If you put something on GitHub, obviously it's in the public domain, and it's, you know, you don't get any feedback whatsoever.
So I didn't understand. I didn't hear like everything. You're cutting a little bit. So I'm not sure what's like actually like the exact question here.
Which do you know of companies where you can upload white papers using quantum algorithms so that you can get some feedback?
No, I mean, no. I don't feel like companies are having a place where you can upload stuff like this. No, you can post something. You can contact researchers like directly, or companies directly. You can post it on GitHub, on Twitter, and try to get some attention and ask people for feedback. But I wouldn't say there's like a centralized place to do this kind of thing.
I really think that the GitHub is the good place where you can share it, and then you can participate in some hackathons, and then people would notice it, because most people go on GitHub. If they see a good repository, they pull it out, they try it. If it works, they like it. I think Kaggle is a nice place, but mostly for data sets. But people there follow also and give feedback on what is posted in their Kaggle repository.
Okay, thank you very much.
Thank you. Okay. Any other questions?
Hi, Michael. Am I audible?
Hi. Yeah.
Could you please describe the interview questions and process at Zapata so that we get an idea about the type of questions that are asked?
Whoa, I'm not sure. But so I went through a couple of interviews with different companies. So I would say the process looks differently at different companies. At Zapata, at least I'm not sure what's the interview process right now, because I'm not directly involved in recruitment. But the one I had was like intro call with, I sent my CV. I had like introductory call. Then I had a second call where I presented a presentation. Then I had on-site interview, and then I got the job. So that was the process. With other companies, I usually had like something like interview and technical interview, depending on the on the company. The kind of questions that got asked. So it really depends a lot on the company and what they're looking for and what's the what's their interest. So I mean, if their interest is mostly on like machine learning, then you will get a lot of questions from machine learning. In my case, I guess they're mostly conversational. So like I tell them what project I did, and they ask me about questions about the project, right? So if I did, for example, solving traveling salesman using QAOA, then they asked me about the project. I told them, and they then asked whether I've learned something interesting about QAOA, or what do I think are the main limitations of QAOA and things like this. So it's hard for me to say like specific examples. As I said, the industry is so young that you won't have like the base of questions like you have for software engineering, like big companies, where you can like see online what kind of questions people are asking. For example, when I was interviewing at Xanadu, I was also like talking about my project, which used in the end like TensorFlow as a backend, and they asked me about TensorFlow and how some stuff works in TensorFlow. So yeah, it's depends. Like there are no easy answers here.
I get your point. Thanks, Michael, for the answer.
Yeah, no problem. Okay, I mean, any other questions?
Yeah, hi, Michael.
Hello.
So, as you said that TensorFlow, so recently Google launched TensorFlow for quantum computing. So, and IBM also as well have a certain platform, cloud platform, in which we can deploy our jobs, quantum jobs, to the cloud and see our results. So, so what do you think we can build certain demo project or some sort of hands-on experience with these frameworks? Yeah, Michael.
Yeah, hello. So I didn't actually understand. I didn't understand like the last part of the question. If you could repeat, that would be great.
Like, so as these companies are building wrapper kind of platforms in which we can do coding like in a software implementation part, like using quantum, TensorFlow quantum. So we build algorithm for different problems. So is it feasible to do mock-up projects using these platform? Is it a good start to do?
I mean, yeah, in the sense that I haven't used all of them, but you have some platforms which are like pretty high level. I don't know, like Penelane or recently TensorFlow Quantum, and you can use them to, you know, play with that, do a project. That's a good idea, I think. I mean, they do a lot of like low-level heavy lifting for you. So yeah, I mean, some of them are some of them are excellent pieces of software. Some are, well, slightly less excellent. That like depends who did them. That there's a lot of that on the market. It's just, you know, that each of them probably has like slightly different use. So depending on what project would you like to do, some might be better than others, but yeah.
So in machine learning perspective, what do you think, like, what is the future of using quantums in using plus machine learning and deep learning? So can we combine these two technologies together?
Oh yeah, I would say there's the whole field of quantum machine learning that deals with this kind of how to, you know, use quantum computers to augment machine learning capabilities. So they're like, as far as I know, the best source of information about this I know is Penelane. So this is a framework, the framework library for doing this kind of stuff, and they have excellent, absolutely excellent tutorials about it. So I strongly recommend it.
Okay, thank you, Mike.
You will probably get the idea. Yeah.
Okay, thank you, Michael.
Okay, so there is a question about starting a company or a startup on the chat. Well, if you know what you're doing and you have enough like skills and time to do that and money, then sure. If not, then not. I mean, depends what you want to do, right? I mean, with with quantum startups, there's like I would say more risk than usually, but it's hard to say. I mean, I wouldn't say that it's a good idea to start a quantum computing startup or a company, or I wouldn't say that it's a bad idea either. You know, it depends. Okay, any other questions? Oh, okay, I see no more questions. Okay, great. So in this case, I think we can finish. So thank you all for listening to me talking. I hope it was, you know, useful and helpful for you. Yeah, I think that's it. And thank you again, the organizers, for, you know, doing this and putting us all together in one place. I would be much more happy if we could now, you know, just go outside, grab a beer and talk. But that's not the case. So
hopefully we can do it someday.
Yeah, I hope so. I hope so. But on the other hand, I guess people are from, you know, pretty faraway places were able to join as well. So that's something. So yeah, thank you very much. Have a nice day.
Thank you very much for the wonderful talk.
So this is started with posting on the Zoom, Meetup session. So whoever missed it, they can see that.
Awesome. Great.
Thank you.
Thank you. Bye.
Thank you.
Thank you. Have a great weekend.